Okay, let's go ahead and get started. So just a quick reminder that the first assignment is due tomorrow by midnight, and then the first hardware lab component assignment is going to be assigned tomorrow and will be due the Wednesday after. I'll say more about the logistics for the lab.
Does that mean tonight or tomorrow?
Tomorrow, 11:59 p.m. Yeah, I guess it would be really nasty if I said Wednesday midnight and I meant today midnight. Yeah, okay. All right. Yeah, I'll say more about the logistics for the lab at the end of the lecture today. So just to remind you of the material we covered in the previous lecture, so we continued our discussion of feedback control. And we introduced some important definitions, some important concepts, trying to formally specify exactly what we want out of a feedback controller. So the first kind of most basic definition that we introduced was that of a fixed point or an equilibrium point. So this is some state which we usually refer to as x subscript 0, such that there's some control input, u0, such that x dot is exactly equal to 0. And I guess I'll put like a 0 bar just to denote that this is a vector of zeros. And a fixed point is somewhere, if you start off there at that state, if you apply that control input, then nothing happens. The state doesn't change over time. And then we discussed some notions of stability. And specifically, we discussed global or local asymptotic stability. And I mentioned that global asymptotic stability implies local asymptotic stability always, no matter what your system is. And for linear systems, specifically, global and local asymptotic stability are actually equivalent. And this is something that you'll get to prove in the assignment that goes out tomorrow. It's not a super difficult proof. And then we discussed this notion of stabilizability. So can we even make our control system locally or globally asymptotically stable? And we saw an example of a linear system in the previous lecture that is not stabilizable. Question? Yes, of course.
Overall, so you have the state of a system, which is just x bar, so that tells us the current position and the velocities.
Yeah.
And then you have the dynamics, which is just the derivative of that, that tells us how the position is changing, how the velocities
Yep.
are changing.
Yep.
And then we have the control input, which is just the result of the actual controller motion.
Yes, it's the thing that the robot is directly controlling. So for the drone, it's the propeller speed,
Right.
for instance. Yeah.
And then, so based on like those things, then given the current robot's like state and dynamics, then you can give it some kind of feedback
Yes.
in order to get it to your reference point.
Exactly. Yep. Yep.
Right. Okay. And so last class there was like a proportional derivatives controller.
Yeah.
It was like this U.
Yep. Yeah. I was gonna just write that down. Yeah.
So that's just the actions that you want the robot to do in order to get it.
Exactly. So that's one choice. So maybe let me just write that down. So the other thing that we discussed is a PD controller, so proportional derivative, a PD controller. And this is basically one specific form that the feedback controller could take, arguably the most popular form. And yeah, the general form is kind of like this. So u as a function of x, this is a feedback controller, equals your nominal control input. So if you're thinking about making the drone hover, that's the control input that keeps the drone at the hovering configuration, plus some matrix k multiplied by x minus x0, and this is matrix vector multiplication here. And this thing is called the gain matrix. And we applied this form of feedback controller to the 1D kind of planar quadrilateral system to stabilize it to its like hover configuration. Question?
So just based on that formalistic feedback, the additional feedback you give it is just based on the reference point,
Yep.
the current state of the system.
Yep.
And, oh yeah, so that's got it.
Yep.
So I was wondering how does dynamics factor in? Does the current dynamics factor into the feedback?
Yeah, so the way the dynamics, so the dynamics doesn't factor into this computation, but this controller impacts the motion.
Right.
So it impacts the dynamics. And so we define this notion of a closed loop system. And this is basically the dynamics you get once you plug in the feedback controller. So we have x dot equals f of x and then u. So if we make u a function of x, so I can write it like this, now the dynamics are purely a function of the state. And so I can just rewrite this as FCL x. Yeah, so the feedback controller impacts the dynamics, impacts the motion of the robot. Question?
But then when it impacts the dynamics, that would impact the current state. right?
Yes, exactly, yeah.
When you go back.
Yep, yeah, exactly. So you apply control input, the drone does something, you look at the state, or the drone looks at the state, does something, so on. And basically the goal that we've set for ourselves is to make that process stable. So no matter where, like what initial state the drone starts off in, we want it to asymptotically converge to the hovering state. I guess what I say to it is like the global version, no matter where you start off, or if you start off close enough to the hovering state, then you want to asymptotically stabilize to the hovering state.
And then stabilizability, so is that, does that only depend on the initial dynamics in the system, or does that also teach?
Yes, good question. So stabilizability has to do with just the original dynamics up there. So stabilizability is asking, can I find some feedback controller? So does there exist some feedback controller that will stabilize the system? So it could be like a really weird, nonlinear like function that stabilizes it, but the question is it possible to stabilize? Okay. So maybe one more question somewhere. Go ahead.
I was wondering what the motivation of linearizing, since I guess it fits with PD control.
Yep.
Well, why exactly PD control?
Yeah. Okay, so we'll talk about that today. I guess that's going to be kind of the rest of the lecture, talking about like PD control like in much more detail and why we linearize the dynamics. I haven't really said why we linearize. Like I just said, it's a useful thing to do. I guess today we'll see why it's useful. And then finally at the end of the lecture, last week we discussed some other considerations beyond stability. Right, so we discussed some of the limitations of just considering stability. We said maybe we want some kind of optimality. We want to expend as little energy as possible, for instance, to stabilize the system. So there's some other performance criteria we want to think about as well. So I guess this is the question we're going to consider today. So how can we both achieve some kind of stability, but then also optimize some performance criterion like energy or time or something like that in a feedback control system. So yeah, I guess the high-level kind of strategy is going to be to take our nonlinear system. So the nonlinear dynamics, x dot equals f of x u. We're going to come up with a linear approximation of it. So linearize the dynamics about some reference point. Again, just canonically, just think of hover for the drone. So we get dynamics like a multiplied by x minus x0 plus b u minus u0. And then we're going to design a feedback controller for this linear system. And the reason is that doing, like designing a feedback controller for a nonlinear system is a challenging problem. It turns out there's much more like well-established and well-understood techniques for designing feedback controllers for linear systems. So we're going to take our nonlinear system, linearize it, design a feedback controller, but then we're going to apply, so I can write down the form of the controller. We'll still end up with like this kind of PD control form. So this kind of feedback controller. And then we're going to apply it to the nonlinear system. Like we're going to actually run it on the physical robot in the lab assignment that goes out tomorrow. And we're going to hope that this works, right? So what we're going to be able to guarantee is that the controller we design stabilizes the linear system. And then we're relying on the goodness of approximation of the linear system to the nonlinear system. And we're hoping that if we can stabilize the linear system, then that stabilizes at least to some degree for some reasonable set of initial states, like it stabilizes the nonlinear system as well. So that's the overall kind of plan. So this maybe suggests why why we're linearizing. It's mostly because that's like for linear systems, we know how to come up with feedback controllers that stabilize them. Okay, so the specific technique that I'm going to discuss is what's known as the linear quadratic regulator. And this is a really popular feedback control design-like method. And it's going to achieve two things simultaneously. For our linearized system. So the first thing it's going to do is stabilize, so actually, let me just say globally stabilize the linearized system. So we're going to achieve global asymptotic stability for the linearized system with this feedback controller that we're going to get from this LQR method. And the second thing is that it's going to optimize some performance criterion. So some objective beyond just stability. Right, so we were saying in the previous lecture, you could achieve stability, asymptotic stability, but it could be really slow, so your drone gets to hover in like a year, which is not a super useful thing. So we're going to introduce this performance criterion that this LQR method is going to try to optimize. Okay. So we're going to start by assuming that we've already linearized our system. So I guess you know how to do this from this week's assignment. So we take our nonlinear system, we come up with an approximation x dot equals a x minus x0 plus b u minus u0 about some reference point. And I'm just going to assume, so this is true for the hovering state, but I'm going to assume that x0 is a fixed point. So we're trying to stabilize our system, our linear system, to this reference point, x0, which is a fixed point. Okay, so just to make things a little bit more kind of notationally compact, I'm going to define this new variable, x tilde. So this is just going to be x minus x0. So the deviation of the state from the reference state. I'm sort of abusing notation a little bit. So this thing is also a vector, right? It's just the difference of two vectors. So maybe I should write like x tilde bar, but that's going to make things messier than it needs to be. So x tilde is still a vector, even though I'm not writing the bar. And then similarly, I'll define u tilde, which is the difference of the control input from the reference, like the nominal control input. So with this new notation, I can write down x tilde dot. So if we look at this definition of x tilde, it's just x minus x0. X0 is just some constant, right? It doesn't change over time. So x tilde dot is x dot. And x dot is just this, the linear dynamics. So a x minus x0 plus b u minus u0. And by definition, x minus x0 is x tilde, and u minus u0 is u tilde. So we have x tilde dot is a x tilde plus b u tilde. So this is just to make things more compact. So instead of dealing with this slightly longer equation, we're going to deal with this equation. Essentially, we've just shifted the origin to x0 and u0. Okay. So, all right. So I guess the next thing to think about is so we definitely want stability, right? We want to come up with some feedback controller that's going to stabilize this linear system. But I said we also want to have some performance criterion, some like objective. So let's think about what a reasonable performance criterion, a reasonable objective might look like. So beyond stability, asymptotic stability, what might we want our feedback controller to do? So I guess one thing we might want is to minimize deviations of the state, so x tilde, from the reference state. Right, so we can achieve asymptotic stability for the drone potentially. So let's say we wanted to hover here. I could say, oh, my feedback controller asymptotically stabilizes the system, but it goes like 20 kilometers away before it comes back. Right, so that would satisfy the definition of stability, but we want to penalize that, right? So we want to penalize like deviations of the state from the state that you want to be in. And similarly, you might want to minimize deviations of the control input from the nominal control input. And loosely, you can think of this as minimizing some kind of effort. So if I want to, again, stabilize my drone, I could ask it maybe to apply control inputs, apply thrusts that are just extremely high, right? Something that's not achievable by the actual physical motors that exist on the drone. So we want to kind of penalize really high control inputs, or maybe even really low control inputs. So just deviations from the nominal control input as well. So if we combine these, I guess any questions on that general motivation? Okay, so if we combine these things, what I could write down, so one potential, I guess, option. So deviation of x from x0, so that's basically x tilde, u from u0, that's u tilde. So I'm going to define this function that I'm going to call j. So j is going to be a function of the initial state, essentially. So the initial x tilde, so x tilde at time 0. So that's the parentheses notation over here. And I'm just going to define this to be the integral. So let me write it down and then I'll explain it. So this notation again, so x tilde at time t, so this is x, yeah, x tilde parentheses c is x tilde at time t, assuming you started off at this initial condition. So the way to think about this is you have some feedback controller. Let's say you come to me with some feedback controller. I'm going to basically tell you how good that feedback controller is. From this, evaluated at this initial, or evaluated from this initial state. So maybe pictorially, I can draw a picture here. So let's say this is the state space. We're picking some specific initial condition, and you come to me with a feedback controller. So I'm going to run that feedback controller forwards in time, I guess all the way up to time equals infinity, so I'm going to run it forever, just conceptually. And I'm going to see how much your state deviated from the nominal state. So that's basically this quantity. So at any time t, we're looking at x tilde, so that's the deviation of state from the nominal state. And then we're looking at u tilde, that's the control input that your feedback controller is applying at that time t. And we're integrating these two quantities over time, going all the way to time equals infinity. Question, please.
Why do we have, so the dot product is our deviation of,
Yes.
but then we have for,
Oh, so, sorry. Just a typo here. Thank you. Yeah, so we have a dot product. So the x tilde you can think of as a column vector. So this transpose is a row vector. So this quantity, just x transpose x, is the norm squared, right? So the distance squared from the distance of the state from the reference state, like that distance squared. And then similarly, we're looking at u tilde, so the norm of u tilde squared. Question?
Professor, the loss function is only a function of the deviation at time 0 because we assume that this is a closed loop system?
Yes. So the way to think about it is that you are coming to me with some feedback controller. So it's some fixed feedback controller. And all I'm doing right now is defining some performance criterion, like something that tells me or tells you how good your feedback controller is from this specific initial condition. And the way to think about it is I'm going to take that system started off at that initial condition, run your feedback controller. So now that's a closed loop system. And I'm just going to evaluate this quantity. So I'm going to look at how much your state deviated from the nominal state, how much your control input deviated from the nominal control input at every point in time, and I'm going to integrate that for all time. And that's the kind of number. I'm going to say this is how good your controller did from that initial state. This is just a definition, right? I'm just like cooking up something that tries to capture this intuition. All right, I guess questions on this. I want to make sure that the definition is clear. So we're integrating a scalar over time, time 0 to infinity. And we're just saying that's how good your controller is at from that initial state. Questions on this and maybe how it connects to this? Yes?
and maybe this is a minor thing, but
Sure.
I would assume that if we really wanted to capture the true definition, we'd have square roots and maybe cube root squared.
Yeah.
But there would be a middle term than that, or omitted, I think, right?
Middle term, yeah, I'll come to that maybe in just a second. Like middle over here.
Yeah, I guess if we were to take the true magnitudes
Yeah.
and integrate, and then if we just wanted to simplify and set square, it would.
Oh, I see. So you want to take the square root, I guess, instead of the, yeah, so Turns out the math doesn't work out as nicely if you take the square root. But that's a perfectly reasonable thing you could ask for as well. Yeah, the math is a lot cleaner for this version rather than the square root version. Good. Other questions? Okay. I guess, does anyone see other issues with this definition that I gave? Yeah, any thoughts on, yeah.
It doesn't like weigh what we care about more.
Yep, yeah, perfect. So we're just saying, just take the distance, right, of the state, from the reference state, the control input from the reference control input, just sum them up, and that's your objective. But we might care about certain states more than others. So maybe we really care, maybe we're operating like close to a table. We really don't want the z dimension to change that much. So we want to say, like, really penalize deviations of the height from the reference height, much more than anything else. Maybe I don't care that much about the speed of the drone, as long as it's in the rough like vicinity of speed equals 0, that's okay. But really, don't make the height move that much. So that's something that we could ask for. Same thing with the control input. Right now, we're kind of assuming that the deviations in state and deviations in control input are of the same scale, but maybe they're not. Maybe you care about some control inputs more than others, and so on. So we can kind of expand this definition. So I'll write down another proposal. So it's going to have the same kind of general form. But I'm just going to introduce two weighting terms. So these are two matrices. So Q is a n by n matrix, where, let me just write it here, where n is the dimension of the state space, and similarly, the little m is the dimension of the control input space. So R is another matrix that's a m by n matrix. Right, so if we do this matrix multiplication, so we have a 1 by n times a n by n times a n by 1. So that's just a 1 by 1 scalar. Same thing over here, 1 by m by m, m by 1, that's another scalar. And specifically, I'm going to, so these Q and R matrices, they're basically user defined. And they have to have some constraints for them to be meaningful. So Q, we're going to assume, is positive, semi-definite. So I'll remind you maybe what that means exactly. And R is positive, definite. And both of these are also symmetric matrices. So Q transpose equals Q, R transpose equals R. And yeah, just a reminder, I guess hopefully this is something you've seen in your linear algebra course. So symmetric, positive, semi-definite matrix. So it's usually abbreviated like PSD, positive, semi-definite matrix. Is one that satisfies X transpose Q x is greater than or equal to 0 for all x. Actually, let me write z just to prevent confusion with the state. Yeah, so matrix Q is positive semi-definite if this condition holds. So any z, if you look at z transpose QZ, that's a scalar quantity. That thing, if it's non-negative for all z, you call that matrix symmetric. Well, assuming it's also symmetric, you call that a positive semi-definite matrix. A positive definite is if this inequality is a strict inequality, so strictly greater than 0 for all z that's not equal to 0. So that's one definition. It turns out that this is equivalent to looking at the eigenvalues of the matrix. And if the eigenvalues are all, let's say, strictly positive, and the matrix is symmetric, then that's equivalent to a positive definite matrix. All right, so I guess why do we need this? So the justification for having these matrices be positive semi-definite, positive definite, is that we want to think about this function as a penalty function. So I guess our job as a feedback control designer is going to be to come up with a feedback controller that minimizes this quantity. So if these terms are non-negative, which is what this condition is implying, if these things are non-negative, then we're minimizing a non-negative quantity, which makes sense. We want to bring that as close to 0 as possible. If you made it negative, then it's sort of like a reward. So we're rewarding the state for deviating from the nominal state, which is not what we want, right? So that's the justification. Okay, let me just pause here for a minute. I guess there's quite a number of things I introduced. Any questions on positive semi-definiteness or like the justification for this performance objective or anything? Okay, so let me just mention that in practice, I'll say a bit more about this later. In practice, the most common choice is to just take the Q and R matrices to be diagonal. And so if you write out this product, all we're doing then is just weighting the different components of x tilde differently. And that, it captures your intuition. We want to just have a different weight on the different components. This form is the more general one, and turns out the solutions we write will work in this more general case, but in practice, almost always have written LQR controllers for many different systems, usually a diagonal choice for Q and R works quite well. Okay. So what is our goal then? We're trying to develop this methodology for coming up with a feedback controller that achieves two things simultaneously. One, it globally stabilizes your linear system, and two, it optimizes, so specifically minimizes this performance criterion, this metric that I've defined over here. And we want to do this for every initial state. So no matter where your drone starts off in, I want to come up with a feedback controller that makes this quantity as small as it could possibly be. So this is a pretty strong thing that we're asking for. But it turns out that, I guess magically, there's a pretty clean solution for linear systems that allows us to do both of these things simultaneously. Okay, so let me, talk about what that methodology is. So the name of the technique is LQR, Linear Quadratic Regulator. And hopefully you see kind of where the name comes from. It's linear because the dynamics are assumed to be linear. Quadratic because this performance objective, this performance metric, is quadratic in the state. Well, really the deviation of the state, like x tilde and u tilde, so that's the Q part. And regulator because we're trying to regulate the state, right? We're trying to get the state close to the desired or reference state x0. yeah, I'm not going to go through the derivation. I'll basically just give you the result. But yeah, I guess the main claim is that we're going to be able to find a feedback controller that has the form that we've seen before. So u as a function of x is the nominal control input plus k. I'm just going to give a little like star here, k star, times x minus x0. So the controller that we're going to come up with will have this form. And k star is just to remind us that this is an optimal controller. Optimal in the sense that this feedback controller will minimize this performance criterion that we've defined from every initial condition. So I guess if you haven't seen this should sort of like blow your mind, right? It's amazing that such a thing exists, like a linear feedback controller of this form, that no matter where you start off, it takes control inputs, it takes actions that will make this quantity as small as it could possibly be. There's no other better feedback controller, better in the sense that you can make this smaller than what this controller is going to make it from any initial state. Okay. So yeah, let me describe the process. Again, I won't go through the derivation. I'll just tell you the procedure for finding this k star that has this kind of optimality property. So there's going to be two steps in the process. Yeah, there's going to be a two-step procedure for finding that sort of magical k star, that magical gain matrix that makes that, optimizes that performance criterion. So step one is to solve the following matrix equation. So I'm just going to write down the equation, and we'll discuss how exactly to solve it in a couple of minutes. So the matrices here, so there's, I guess, the Q matrix is exactly that Q matrix, so that's part of the problem definition, right? We as the user, we're going to specify the Q and R matrices that basically say exactly how we want to penalize deviations in the different components of the state or control input. Same thing, Q and R matrices, so those are given by the user, by us. The A and B matrices, those are the A and B matrices that define the dynamics, the linear dynamics. So the only unknown here is S. So this is a n by n matrix. You can kind of check, maybe offline, that the dimensions match up. So the 0 here is also a matrix. This is a n by n 0 matrix. Q is a n by n matrix, so at least that checks out. Right, so the only unknown matrix here is the matrix S. I'll say exactly how to solve this equation in just a little bit. But let's just say somehow we can find some S that satisfies this matrix equation. So the solution, we're going to call that S star, just like denote by S star. And yeah, I guess just to give this thing a name, so this matrix equation, so it's called the algebraic Riccati equation. Or just the Riccati equation for short. All right, let me write down step 2. Yeah, I can erase this. So yeah, step 2 is simpler. So I'm going to define something that I'll call K star. It's minus R inverse B transpose S star. And this is just matrix multiplication, so everything here is known. Right? So assuming we've done step 1, we found some S star that satisfies this Riccati equation, we can just plug that in. So multiply that by minus R inverse. R again is that matrix over there, B is part of the dynamics transpose S star. And we're just going to give that a name. We're going to call that K star. And then our feedback controller is going to be U. Let's think of it as a function of x tilde first. So I'll define this to be K star x tilde at some time t. And we can just expand this out a little bit. So U, sorry, it should be U tilde. U tilde by definition is U minus U0. X tilde by definition is x minus x0. So U tilde is U minus U0. I'll just bring the U0 on the other side. So U as a function of x equals U naught plus K star, and then x tilde is x minus x0. Right, so these are just equivalent. I've just expanded out the U tilde and x tilde to get to this. Okay, so what I want to do is just briefly recap the steps. So I haven't yet talked about how we solve this equation, but just imagine we can. We get S star, we plug it in to compute this K star, and that's our gain matrix. And we end up with this specific feedback controller that depends on 4 things. So it depends on A and B, the dynamics, and then Q and R, the matrices that define our objective. What I want to do is just make sure that the claim I'm making is clear. So I haven't proved this claim, and the proof takes a lot of work. I won't go through that here. But I just want to make sure that the claim is clear. So what I'm claiming is if you go through this procedure, you find this feedback controller. It has this magical property that no matter what initial condition you start off your drone or whatever robot system in, at least this linearized system, and if you apply this feedback controller, it minimizes this metric, this performance criterion that we defined. And there's no other better feedback controller that anyone could come up with that makes this quantity lower than what this feedback controller makes it. Questions?
So A and B are probably linear.
Yes, yeah, A and B are the matrices that define the linear dynamics. Another question?
Can you talk more about Q and R and what they represent, and
Yeah.
specifically since they're user-defined,
Yeah.
how you generate those?
Yes, good. So I'll spend a few minutes talking about the more intuition for how to specify those. For now, just think of them as some matrices that tell you how you want to weigh deviations in different dimensions. I can give a quick explanation maybe here. So if we choose Q to be diagonal, let's say, so we're going to have different components of x tilde. So I've already transposed x tilde. So let's say I choose Q to be this diagonal matrix. So if I multiply this out, what I'm going to get is Q11 times x tilde 1 squared plus Q22 times x tilde 2 squared, and so on, Qnn x tilde n squared. And so this matrix, like the diagonal elements of this matrix, are telling me, are giving, like specifying weights for how much I care about the first component of the state, let's say deviating from the first component of the reference state, the second component of the state deviating from the second component of the reference state. So if I make Q11 large, I'm basically saying try to make Q1 tilde squared small. So don't deviate too much in terms of the first component of the state. So that's roughly the intuition for what they mean. Exactly how to choose them, I'll spend some more time talking about it in just a few minutes. All right, other questions? Okay, is the claim clear? So like what I'm saying this feedback controller does? Yes, please I'm nodding. Okay. Anyone not clear on this? I'm happy to explain. Okay. All right. Okay, so I guess just a couple of comments on this. So the first one is just how do we go about doing step one. So we have this matrix equation that we need to solve. So I won't go into the details, I'll kind of give you just the process. So yeah, there are like built-in like Python or MATLAB. We won't use MATLAB in this course, but just in case. Functions for solving this matrix equation. And then I guess for doing that, step two as well. So yeah, essentially there's just a function you can call like LQR, and you give it 4 arguments, 4 inputs. So A, B, the matrices that define the dynamics, Q and R, the matrices that define our objective, and it solves this matrix equation, this Riccati equation for you, and it gives you the K, let's call this K star, S star as well. So under the hood, there are some numerical like techniques that go into solving this. The thing that makes this tricky to solve is that this is non-linear. So if you look at the form, there's a quadratic dependence on S, right? So there's a S and then there's another S in the same term. So this is not just some like linear matrix equation that you can solve easily, but there are nice numerical techniques that solve this that are implemented in MATLAB or Python. Yeah, it turns out there was a bunch of research on like how exactly to solve this matrix equation, I think back in the 60s or something, and my understanding is there's like one paper that basically just like solved it, and then no one really did much research after that because the numerical techniques are so nice. Okay, so that's basically the process that we'll use, just calling the built-in MATLAB or Python functions. Just one note as a warning. So Python, and I think MATLAB as well, uses a slightly different sign convention. So their controllers, the convention is that it's U tilde is minus K star X tilde. So there's a minus sign over here. So for the crazy fly, I guess that's the convention that we're going to be using. But the output that you get from the built-in Python function assumes this is the form. So you just have to take the K star that you get from the Python function and just negate it. Yeah, I'm mentioning this because if you don't negate it, that's going to make your drone unstable, which is not what you want. We'll remind you in the assignment, but just beyond this course, we're using like these functions. Just remember that the sign over here, the convention, is important. Okay. One more thing I want to mention before talking about how to, actually I'll leave this up here. So far I just presented this kind of as a black box like technique. You solve this matrix Riccati equation, you get this K star in this following way. But there's actually a nice interpretation that this matrix S star, which is the matrix that solves or satisfies the Riccati equation. There's a nice interpretation for it. It basically gives us the optimal cost. Actually, sorry, there was one more piece of, here it is now. Okay, so that function which we define, I won't write it down again, but like j, which is a function of x tilde at time 0, we defined it to be this integral. So that function j is called the cost function. So that's just the name given to that function, cost, because you're paying a penalty for deviations in the nominal, sorry, in the state or the control input. Yeah, so it turns out that the solution to the Riccati equation, this S star, allows us to calculate the optimal cost for any initial state. So you could do it the way I was telling you before, like you take your controller, you start off your system from some initial condition, you run it for like all time, like 0 to infinity, and then you do this integral. But that's not, at least the way I described it right now, like to simulate your system, you have to simulate it for all time. Turns out there's a kind of shortcut, which comes from this solution to the Riccati equation. So this is another claim. I'm not going to prove it. I'll just state the claim. So the j star, so the optimal value of the cost function from this initial state is equal to x tilde at time 0 multiplied by s star multiplied by x tilde at time 0. So this matrix S star basically does the integral for you. So you don't need to somehow figure out how to complete that integral. That's a claim, I'm not proving it, but it's true. So you just take your initial condition, you multiply that, well, transpose of that, multiply that by S star, and again by the initial condition. And this quantity is a scalar, so S again is a n by n matrix. This is with the transpose, it's a 1 by n. This is a n by 1. So this quantity on the right hand side is the cost that the controller, this LQR controller achieves from this initial condition, and that's the optimal cost, as I claimed before. Question?
So then what does K star give us?
So K star gives us it specifies the feedback controller. So when we actually run the drone, let's say, we're going to program in that specific K star that we get by solving these two steps, like the Riccati equation and step 2. So there's going to be some actual numbers. So when you linearize the dynamics for this specific drone, you have a specific A and B. We're going to specify specific Q and R, as I'll describe in a bit. That's going to give us some specific numbers for K star, and that's the controller we're going to run on the drone. Question back there?
Yeah, when you talk about cost, you're
Yeah.
taking deviation of the function j, the performance metric?
Yeah, so this function, so we're thinking of j as a function of the initial state. The name for that function is cost function. So I guess that's all I meant. But yeah, the reason it's called cost function is because the thing that it's measuring is deviations of the state from the nominal state and the control input from the nominal control input. Yeah.
about the cost function and how it relates to LQR.
Yeah.
First being, if the cost function does not converge because something could be infinite.
Yes. Okay. Okay, yeah, so I haven't, that's a good observation. So right at the beginning of the lecture, I said we were going to do two things simultaneously. So this LQR process is going to do two things simultaneously. One, which I kind of claimed explicitly, is that it's going to minimize, like optimize this performance objective, performance criterion that we defined. The second thing I claimed is that it's also going to stabilize your your linear system. And that basically implies that the integral is always well defined. So if your feedback controller was starting off here and then blowing up, like not asymptotically stabilizing the system, then this integral could be infinite. If your system is stabilizable, then this LQR process, will find this feedback controller that will stabilize your system in addition to minimizing the cost function. You got one more
The
question?
second one is, I guess, like, with cost functions, often there is this idea of a discount rate as well.
Okay, yeah.
In the future, and like, even if you have a system that stabilizes that a lot.
Yes, good question. So I won't talk about that here, the idea for a discount function is maybe I care about things that happen soon in the future, and I don't care too much about things that happen like far away in the future. There are ways to modify this to take that kind of discounting into account as well, and you can still solve like this LQR process and get a controller. It's just slightly more complicated, but you can do it. Good. Other questions? Okay. All right. I think let me just state this second. I kind of said it verbally, but let me just state it a bit more formally. So hopefully the optimizing the performance criterion part is clear. Let me just say explicitly. So the K star that we get, so K star from this LQR process stabilizes, and by stabilizes I mean globally, asymptotically stabilizes the linear system. So we can look at the closed loop system. Right, so we had, the original linear system was x dot equals ax minus x0 plus b u minus u0, or equivalently, x tilde dot is a x tilde plus b u tilde. So if we plug in this feedback controller, I'll do it for the tilde version, so we get x tilde dot is a x tilde plus b u tilde, which we're saying is k star x tilde. So I can combine some of the terms here. So a plus b k star x tilde. And this is x tilde dot. So this is our closed loop system. So the system that we get, the dynamics that we get when we plug in u tilde is k star x tilde, k star again from this LQR process. And what I'm claiming is that this closed loop system, assuming your system is stabilizable in the first place, if it's not stabilizable, then there's nothing you can do to stabilize it. But if it is stabilizable, LQR will find a matrix, or the matrix that you get from LQR, the K star matrix, makes the closed loop dynamics globally asymptotically stable. And again, I'll just emphasize this is for the linear system. We haven't said anything yet about the nonlinear system. We've just linearized our nonlinear system, and then everything henceforth was for the linear system only. Okay, I guess questions on the stability claim? Okay. All right, and I'll just like sort of throw in a caveat again. So I haven't proved any of this, right? I'm just like claiming a whole bunch of stuff, and you're taking my word for it. If you are interested, I can point you to references that go through some of the proofs. The proofs are, yeah, they take a while to really do. It'd probably be like multiple lectures if you wanted to see the proofs of all of these things. Okay. Okay, so let me go back to the question that someone at the back asked. How do we actually choose these Q and R matrices? I just said they're like user defined. I give you some intuition for what they mean, but yeah, how's it going to work in practice? And I guess how's it going to work for the first lab? So in theory, any choice of Q and R, as long as they're like positive, let's just say definite for the sake of simplicity. So any such choice of Q and R will stabilize, so globally, asymptotically stabilize the linear system. Right, so this is just a theoretical result. No matter what Q and R I pick, the LQR process will give you something that stabilizes the system. In practice, it's not so simple. And that's kind of the point of the first lab, is to see in practice that it's not as simple as the theory maybe makes it seem. So in practice, there's a whole bunch of factors that make things not ideal. So the first one is that the system is not linear, right? So the drone dynamics, we wrote it down. We have like nonlinear dynamics. So what we're relying on is like the linearized system being a good approximation of the nonlinear dynamics, which it should be in some region around the hovering state, but if you deviate too far, it's not necessarily going to be a good, like the first order Taylor series expansion is not necessarily going to be a good approximation. So yeah, that's one kind of one source of non-idealness. The other one is that there are some imperfections in our dynamics model. So from this assignment that you're doing now, you're calculating the thrust coefficient and the moment coefficient. Those are like empirically observed, right? So we did some experiments, putting the drone on a thrust stand and calculating and running a bunch of experiments. So these are like approximate, they're not exactly describing the dynamics, like the full like aerodynamics of the propellers and so on. So there's some like model mismatch. And then there's also some state estimation errors. So in order to implement that LQR controller, we're assuming that at every point in time, the robot can exactly sense its state, right? So the right-hand side over there requires like the state. In practice, that's not exactly true. The robot has some sensors, like a IMU, inertial measurement unit, a bunch of other like sensors, like a downward-facing camera and so on, that are estimating the state, like estimating the speeds, the orientation, and those are not exactly the physical state of the actual like, system. So there's some like estimation error as well. So yeah, in practice, what you'll find is that some choices of the Q and R matrices are better than others, and that's basically what we're going to do in the first hardware assignment. So we're going to give you, so we've already linearized the dynamics of the drone, so that part at least is, well, will be done by midnight tomorrow. So you'll have the A and B matrices, and then the first lab, you're going to tune the Q and R matrices. So we'll give you some poorly tuned Q and R matrices, that are not going to make the drone like crash completely, but then like it's going to like, not be really like stabilizing to hover. And your job is basically going to be to choose the QNR matrices in a way that results in good like performance on the physical drone. So I just want to give you some like intuition for how that tuning process might work. So yeah, so that's why I kept this matrix, these expressions up over here. Again, in practice, you're just going to choose diagonal QNR matrices. So let's just look at the Q part for a bit. And imagine that you've chosen some specific values for that Q matrix, maybe just the values that we gave you as default. But then you see that the drone is like drifting in Z. So there's, I forget exactly what the height is. I think it's maybe a meter or half a meter off the ground that the drone needs to stabilize to. Yeah, imagine that it's kind of like just going like this up and up, and maybe it like stops somewhere over here, like way above the, let's say it's 1 meter height that you want it to stabilize at. So how would you go about updating the Q matrix? So this Q matrix again is a 12 by 12 matrix. We're going to just choose it to be diagonal. So any thoughts on what you would do? What do you try next? Like what's the update to the Q matrix that you might try? Go ahead.
Just increase the weight for Z.
Yeah, good. So increase the weight for Z. And I guess which of these? Yeah, the third component. So the 3-3 component. So if you remember the state vector for the 3D drone, so it's x, y, z, roll, pitch, yaw, x dot, y dot, z dot, and then the angular velocity components. So yeah, if you see the behavior that I was describing, then you take the, so this is the Q11, Q22, Q33 up all the way to Q12, 12. Yeah, so you take this element, the third element, and you crank that up. So maybe let's say by a factor of 10 or something. And you see what that does. And you should see that it stops like exhibiting that behavior. So it should now like penalize the Z height much more. But suppose now you start seeing, like once you do this, you try it out on the hardware system, and you start seeing it do this. So it kind of just like oscillates. So it's doing a reasonable job on average, I guess, of being like around 1 meter above the ground, but it's oscillating like this. So what's another thing that you might try next, like updating the Q matrix? Good.
Penalizing the Z acceleration.
Yeah, so not quite acceleration. So the state vector, yeah, only has the speeds. Yeah, so that's exactly right. So you penalize the Z dot component of the state. And the intuition is from the previous lecture, right? So if you go back maybe to the notes from the previous lecture, when we just had the proportional controller, so your feedback controller that just depends on the Z position of the Z dot, there's no damping, right? So it's kind of, it behaves like a spring mass, like oscillator without any damping. So if you add a component that penalizes the Z dot as well, that basically adds in like a damping term. So that, let me just write down the state again. So X bar is X, Y, Z, roll, pitch, yaw, and then X dot, Y dot, Z dot, and then PQR. So it's the 9th component, right? That's the Z dot component. So you crank that up. Yeah, and then that's kind of the intuition. So you see like roughly how the drone is behaving. You figure out like what should I penalize more, and then you penalize it. The control input part, the R part, yeah, we can think about that as well. So let's say that the drone is like not really doing like anything. So it's like deviating like far from the state that you want to be at, and it's basically like nothing is, no state is like being like tracked particularly well. So what do you think you would do then? And just as a hint, this is like modifying the R matrix, the control input part. Go ahead.
Probably like to reduce penalties on control.
Yeah, so you reduce the control penalties, you bring R down. So let's say you just divide R by a factor of like 10. So that's going to be the process. And yeah, the goal with this is to just get familiar, like see that the theory with the linearized system and so on like doesn't quite match reality because of all these factors and other factors. Yeah, this is sort of like an art form. Like you'll see that it takes some tuning and you build some like intuition for what LQR is doing. Okay, let me switch to the slides just to give you a sense for what's possible with LQR. So I have a bunch of videos of LQR working in practice for different systems. Okay, anyways, yeah, I'll just verbally describe what the plan is. So we have 2 lab spaces reserved for this course. So one is G105, that's in the E-Quad. The other one is ACEE012, Andlinger Center. Those are both, I guess, on the slides, and I'll maybe send a Canvas announcement as well. They have like netted arenas. So the Andlinger space has 2 netted arenas. The G105 space has 1. G105, we have 4 desks that are reserved for this course. So they're kind of on the left part of the lab. It'll be pretty obvious. Those are the ones that are clean. The other ones have a bunch of other equipment for other courses. So you're welcome to use the 4 desks that we have reserved for this course. Everyone should have access to both spaces. So you might just have to go hit a hotspot to update your Tiger card. But as soon as you do that, you should be all set. And I think everyone has completed the online safety training, so you should have access to the lab spaces. And I think there's some like hours on the lab spaces, so you can use the hours. You can go in like whenever you want. Like your team for the assignments can go in whenever you want. And I think it's up to like 1 a.m. or something like that you're allowed to use it technically. And then 1 a.m. through, it's either like 6 or 7 a.m. you're not supposed to use it, and then 7 a.m. Onwards again you can use it. Yeah, and then I guess you'll do the assignments in teams. So just go to the lab space with your teams. In the Andlinger space, I think around like 5 or 6 teams can work relatively comfortably. So there's no sign-up sheet. So we tried a sign-up sheet in the very first year we offered this course, and we found there was a mess. Like people were signing up like 5 minutes before a time slot and just showing up and saying, hey, like we signed up, even though it was just 5 minutes before. So there's a kind of like organic model that we found works better. So just show up there. If there's like multiple teams that are working at the same time, just share the space. So with this LQR lab, it's kind of like an iterative process. You'll tune the controllers, you'll go back and like try it out on the actual system, you'll think some more, and maybe while you're thinking, you can let another team try out their controller costs or gains on the hardware. So that's roughly the process that we'll follow. And then, we've described exactly what you'll submit in the assignments. It's basically a video and some logs showing that you've successfully made the drone hover like pretty well anyway. All right, questions on this? Go ahead.
Will we have access to labs after this?
After the semester, no. Yeah, so just for this semester, yep. Other questions? Okay, so I'll see you on Thursday.